I'm going to get what? In other words, I can make this inequality even more stronger, weaker. Okay. 0 and by r close to 0 and by r and its closure. Okay? And what finally this means? Okay, if this is true actually, just think about it. Are we in the assumptions of this theorem? Think about it. If this is true, are we in the assumptions of this theorem? So let's take an element from here. So it's like, let's take a G from this closed ball. So if the G is from closed ball, the norm of G is less than or equal to 1. Okay? For this G, I can find F and F, okay, with some norm, okay, so like a less than or equal to A, such that the difference is less than or equal to what? Q. So just think about it. So if G is here, and if this is true, then this G must belongs to this closure actually. Okay? So if G belongs to the closure of this set, it means that there is a sequence, okay? There is a sequence of elements in this set, like without closure, such that that approximates your G. Okay? And that sequence is going to, because it is in this set, so it's going to satisfy this inequality with n over r. Okay? And this would be also satisfied. Why? Because they are approximating your G. Think about it. They are approximating your G. So it's like a TF is going to be TFN, and your G is going to be G. Okay? And less than or equal to Q means that you can make it smaller as much as you want actually. So you are in the business of this theorem. So in other words, if you want, you can precisely put, so it's like it's a pretty good way to basically reinterpret the same condition here actually. So if this is the case, if this is true, are we happy with that? Why those conditions are true? Just think about it. Take an element from here. Say, call it H. So what does this shows? So H is in F, and norm of H is less than or equal to. Agree? If this containment is true, this H is also going to be in this closure. So if H is in the closure of this set, it means, okay, that there exists a sequence of elements here. What would be that sequence of elements? So it's going to be something like TFN
with norm less than equal to
okay,
n by r.
with norm less than or equal to what?
N by r.
N by r, which is like your A, such that this sequence approximates your H actually, the thing that you picked. And by approximating H, what I mean, that the difference between TFN and H can be made as much as small I want actually. So in other words, this inequality is also trivially satisfied. So TFN minus H is less than or equal to TFN. So you are in the business of theory. So maybe this could be a good exercise that if this is true, then why that inequality is true actually. It's not that difficult, but you can make sense of it. So if this is the case, if for a given G, this assumption is satisfied, okay. So it's like if these assumptions are satisfied in case of the given situation that you have, then what does the result is telling us? The result is telling us that for every G, I can find an F, okay, which can serve as a preimage of G, okay, and F and G are related with in this manner actually. So this really completes the proof actually. Okay. So by last lemma, we are done with the proof. So by last lemma, we get our conclusion. We get our conclusion. Is it making sense? So the open map theorem is true. Are you happy with it? Okay. So whenever you are reading these proofs or such proofs, if we want to learn things correctly, okay, then we don't need to cheat ourselves. In other words, make sure that you understand every single step. You understand that why that works. Okay? And also try to keep a bigger picture that how the proofs are being done actually. Okay? What is the method actually? What are the tricks? Because when you want to prove your own results, at least at the basic level, you have to use the similar kind of tricks. It's not going to be much different from the things that you are doing here actually. Okay? Unless you are doing something exclusive, then you have to come up with, out of the box. Alright. So now I like to do, finally, a last result for which I don't need to prove any lemma. It's a good news. And it has a 3-line proof. Okay. And it's called the closed graph theorem.
theorem का बता dilemma है nut bolts
One of the good thing about this book is that his mostly proofs are non-classical actually. He's not giving the classical proof, he's giving the modern proof actually. Okay, always like a variation of the state-of-the-art proofs. So it would be also a good exercise for you guys. I mean, if you are really interested in, learning things, to go for the classical proofs as well. If you understand this, you can surely and certainly understand the classical proof of that actually. So it would be a pretty good exercise to see, say for example, uniform boundedness principle proof, okay, not from this source, but from some other source actually, and maybe one good source could be this book by Alan Krasik actually. Okay. So it's like introductory function analysis. It's a pretty detailed and nice book, and it's a with application. Okay? So it's like whenever, especially in South Asia, whenever you ask from them, what's a good book on function analysis, then people will come up with this statement. From where you have learned function analysis, they're going to say crazy. Okay. Okay. So it's worth, looking book. I didn't choose this book because it's not focused. So it's a huge book covering diverse amount of data. Okay, it's like a results where I'm interested in like pretty focused things actually, especially those which are important for what do you call PD thing. Anyway, it's a nice book. It's a nice book. But interestingly, he writes more details than this. It's a good thing. Anyway. So, before stating the results, so we are moving towards the third conclusion. It's called the closed graph theorem. And we can prove this result before the end of the class. Okay, you're gonna get a few minutes. So it's a small result. It's not a big deal. So what we have done all the labor that we need to previously. Closed graph, but okay, so it's like a closed graph. But what's the meaning of a graph? What's a graph is doing here? Okay, what's the meaning of a graph for a function in maybe calculus that you know? What's a graph?
A visual representation. A visual representation.
I'm asking for a precise definition, not a.
Cartesian coordinate points.
Okay, it's a collection of the points. So it's like if I have been given a function f of x, okay, roughly, then a graph is what? How can I write graph as a set?
X comma f of x.
Yes, it's a collection of x, f of x, such that x is in the domain
D.
of t. So that's a graph of the function. That's the meaning of a graph. Okay. Now, here we're not in 2 dimensions, right? We are in higher dimensions. We can use this analogy to use, what do you call it? Define the graph in such a way. Alright, so imagine t from e to f is linear. I'm not writing the statement, I'm just defining graph. And what is the meaning of closed graph? So t is linear by graph of t. Okay? I mean the collection of ordered pairs. So it's a collection of ordered pairs f and tf such that f from ex. So that's a graph. Okay? And by a closed graph, I mean this graph is a closed subspace. So this graph is closed if if this graph of t is closed subspace of
E cross F.
subspace of
E cross F.
E cross F. Okay? But this raises new questions actually. What is E cross F? Is it a normed space? If it is a normed space, what is the norm on this actually?
No, both by both. Gene root theory में
Alright.
standard.
What would be the norm? Product norm. So give me the definition of a product norm. So in other words, I would like to define what is the norm of fg, for example. Here. So what do you think? What's your guess that it should be what? Multiplication of norms. Any hint?
So two norm close under will require
So the best is that
Norm of f
the norm of f
E.
okay, plus the norm of g.
plus
So it's like a f is a norm in E,
but this is an G
norm in f.
root में डालें.
Okay?
define this.
Yes.
Square
And you can prove that it's a normed space.
root में.
Technical properties.
Uh-huh.
By satisfying all properties.
by satisfying all properties, because E and F are normed spaces. So it would be a pretty good exercise, and there is an exercise like that here. Okay? Good. Now can we define the closeness of this norm? Or if I would like to have a norm on the graph of T, what would be that norm? What do you think?
It would be
Equals to F plus
P same norm होगी.
similar.
norm
Okay.
plus
So if this is the case, let me ask something from you. What would be the meaning of closeness of the graph? How can I define precisely?
Initial and final points be finite. Initial and final point of graph.
No, what
So,
so closeness topologically?
a sequence converging.
Yes, a sequence. So how should I write it?
limit size.
What should I write it?
Consider a sequence that is
So
convergent.
if I consider a sequence Fn, okay, and Tfn that converges to Fn Tf, okay,
Then
TF.
हाँ?
सर वो तो शो करना कि वो TF होगा.
क्या मतलब? No, for the closeness we need to take a convergent sequence, but we have to show that this
Yes.
belongs to
Yes.
indeed.
Yes, yes.
Okay, that's what we have to show.
F and TF.
And I can break it down even more actually. I can break it down even more. I can say that, graph of T is closed if I have a sequence Fn in E such that F,
TF and
converges to F and
TF and
Tfn
Converges to
converges to
TF.
some G, for example. Okay? So these both implications imply
G
that this G must be TF. Okay? And what does this show? That, F and TF belongs to the graph of TF. This is what that it shows, essentially. So in other words, if this condition is satisfied, your graph is closed.
So sir, whenever T is linear and bounded, graph of T will always be closed.
Yes. 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 Anyway, so now I like to write, what you call the closed graph theorem. It's two-liner proof. So the closed graph theorem tells me, okay, and it's precisely the statement that you told me. It's like a bit more weaker actually. So the closed graph theorems tell me that if E comma F are Banach and T is linear, okay, then T is bounded if and only if graph of T is closed. That is what essentially you have to do. So it's if and only if actually. Okay. If T is bounded, then graph of T is closed actually. Okay. We'll finish in assigned time. But let's finish it quickly. Okay. Alright, so here's a proof. So define a norm. Okay, so 3 lines. By norm of f plus norm of Tf in E, and this must be obviously in F. Okay, and I can show that this is a norm and so on and so forth. But what follows immediately from this norm is that this can be estimated by norm of F in E actually. No,
other way around.
must have other way around. This,
एक term खत्म.
ठीक है? Now if the closed, okay, so this norm is norm on what? So it's a norm on graph actually. Okay? So it's norm on graph. So if this is a norm on graph, and graph is a closed subspace of E cross F, okay? So if E and F are complete, we can also show that E cross F is complete actually. Okay? So if E is complete, F is complete, E cross F is complete. And I have a closed subspace of a complete or of a Banach space. So the graph would be complete itself as well. Okay? So as both, and this is an exercise as well, as both E and F are complete. Okay? Is this a norm on graph or norm on E? Norm on E. Okay? So this E and F are complete. Then E is complete with respect to this norm and corollary 15 by 10. What's a corollary 15 by 10? Yes, corollary 15 by 10. It was the corollary that said that if you have two Banach spaces, okay, which is complete with respect to two norms, and one can be estimated by other, okay, so there exists a constant C, non-negative, such that the norm of F, okay, can be estimated, okay, by C norm of F. It is something interesting. This is also bigger than or equal to TF. Okay? And this is true for all F in E. And my claim is that this is enough for proving what we want. It shows that T is bounded. One side is trivial, the other side you can do it in this manner actually. So in other words, try to write a complete proof. There are gaps here. Okay? So try to finish up the proof in detail. If you have questions, you may ask. And that's the end of this chapter actually. Okay? For the next chapter, we will just spend one lecture on next chapter, and then I would like to go for the previous chapters that we left.